Hi everyone and welcome to the new video. You probably heard that bananas are naturally radioactive, but can we see it in action? Well, we know that bananas can be radioactive because they contain potassium. Can we measure it? In this video I will measure the radiation of the bananas using several radiation detectors, and for the comparison I will also measure the pure potassium and I will compare it to the radiation of the real uranium ore. It can be fun. Without further ado, let's get into it. First, I'm selecting the bananas in the supermarket and I will try to find the best one. Hopefully it has the best radiation. By the way, do I need to wash the bananas before eating them? I never do it, but apparently it is an open question. What do you think? Feel free to write in the comments below. For the measurements of the bananas I will use 3 radiation detectors. Here is the Radioactive scintillation detector and here are 2 Geiger counters. The first one is less sensitive and the second one has a better sensitivity with a pancake-style detector. Now all the detectors are measuring the background radiation in my house, and let's measure the bananas. Here I configured all radiation detectors to show the values in microsieverts per hour. I don't need to wait for an hour, but at least 1-2 minutes is recommended because it's sort of a moving average. Okay, some minutes passed and we can check the results, and we can see the result is interesting. We see no difference. How is it possible? We know that the bananas can be naturally radioactive because of the potassium, but why we cannot see it? Is the radiation detector broken? Well, all 3 cannot be broken at the same time. The reason is something different. Let's figure it out. First, let's figure out why bananas are radioactive. As mentioned before, bananas contain potassium, and the potassium naturally occurs in 3 forms: K39, K40 and K41. And only one isotope of potassium, K40, is naturally radioactive. And the interesting thing is that the fraction of K40 is only 100%. Practically it's only 0.0001 fraction of the mass. And the second thing is that the average banana contains about 400 milligrams of potassium, which is less than a half of a gram. Now we can see why it is incredibly hard to detect the radiation of the banana. Not only the banana contains less than a gram of potassium, but the potassium itself has a 0.0001 fraction of the radioactive material. Practically this small value is just not visible compared to the fluctuation of the natural background radiation. Ideally we should have a special lid box to cover all the background radiation and only then we can see something. But there is an easy way. We can just buy a pure potassium in the store and measure it. Let's do it. Okay, as a second experiment, let's measure the radiation of the potassium. The pure potassium is a metal and of course I cannot buy it in the supermarket. Instead I bought a pack of these pills with potassium and magnesium. It is intended to be used as a food supplement. Maybe it works. According to the description, each pill contains about 200 milligrams of potassium and there are 180 pills, so it should be definitely more than in a banana. Let's start the measurements. The first radiation detector is a budget one, and the challenge is that the potassium is mostly a beta emitter. As we know, there are 3 types of radiation: alpha, beta and gamma. Alpha is a heavy nuclear, beta is electrons and gamma is photons. Potassium does not emit alpha radiation, it mostly emits beta and a bit of gamma. And here the challenge is that the budget radiation meters are mostly suitable for gamma, they are not really sensitive to beta. And indeed I placed the radiation meter on the pack of the potassium and I don't see significant results. There are some changes, but they are mostly caused by the natural radiation background. And it is actually interesting that the background radiation is not a constant, it is always changing. Here is a graph of the background radiation that I have in my Home Assistant, and as you can see there is a natural variation in it. And compared to this variation it is actually hard to see the small change caused by the potassium. And now let's test the second one. This is a much more sensitive detector that has a better pancake-style Geiger-Müller tube. And as we can see, the result is much better. We can see a real difference. When I put the detector on the pack, the values immediately start to grow. So we can confirm that the potassium is really radioactive and we can see it. But this radioactivity is not high, and of course this pack contains a package for like 3 months, so getting 1 pill is absolutely not dangerous. If I will eat them all in one day I will probably be sick, and not because of radiation. And even more, according to Wikipedia there is about 140 grams of potassium in every human body. So technically our bodies are also naturally radioactive, so there is no reason to be afraid of potassium. As a next test, I can use a radio code scintillation detector. It allows us to detect which elements are inside. Of course, we know that it is potassium, but we can confirm it. So I put the detector for several hours, and here we can see this peak on the spectrum. And as the Android radio code app shows, it is really potassium, so it is good to know that we can confirm it. This is the power of the scintillation detector. It can not only detect the radioactivity, but it can also show us why the object is radioactive. As the last part of this video, let's compare the banana radiation with some real radioactive minerals. And by the way, there is even an informal measurement unit called banana equivalent dose. And now I will take two uranium minerals and we will see how radioactive they are compared to a banana. The first one is a torbernite from France. As we can see, it is a nice specimen. I keep it in a jar because it looks fragile and I don't want these pieces to fall down and contaminate the surround environment. It looks like a sort of classical radioactive object, it's a green one. However, it doesn't glow in the dark and it doesn't glow in UV. Interestingly, its radiation pattern looks a bit like a banana. It emits not so high gamma radiation, but a lot of beta, as we will see, and let's do the measurement. First, how do I know that it is a beta? It is easy, as we can see most of the radiation is blocked by the wooden jar lid, and gamma radiation would not be blocked by wood, so it is beta. And second, let's compare how high this radiation is compared to the banana. An equivalent banana dose is 0.1 microsievert. Let's do a simple math. Here we can see about 260 microsieverts per hour, which corresponds to about 4 microsieverts per minute or 0.07 microsieverts per second. So as a rough estimate, this piece of torbernite gives us an equivalent banana dose in a second. This sounds impressive, but in reality the banana dose is just low, this specimen is not dangerous. Practically I need to keep this specimen in the hand for a minute to get an equivalent dose of 1 dental X-ray. So it's not dangerous, it's safe to keep this mineral in the cabinet because the radiation is detectable only near the surface and it's also mostly blocked by the jar lid. And now I will show the second mineral. This is uraninite from the United States. And as you can see, it's pretty radioactive for its small size, so the radiation density in this mineral is much higher than in the banana. But it is still interesting to see that all these three elements, banana, torbernite, uraninite, all of them are natural, they are not from the nuclear reactor. Of course, I bought these minerals, I did not walk in the mountains with a geological hammer. But technically these minerals are not artificially produced, they can be found in nature. As a small mathematical task, I will ask viewers to calculate the banana equivalent dose of the uraninite. Write in the comments below your answer. In the same way as for previous mineral, this uraninite is not dangerous, it's safe to keep it in the cabinet. The radiation is mostly detectable on the surface, so there is no danger. Okay, that's it for this video, I hope you learned something new. In this video I measured the banana radiation and compared the banana equivalent dose with some real radioactive minerals. In the next video I will explain the radiation measurements in more details, it can be fun to see. And by the way, if you want to support this channel, feel free to visit my Patreon page. This support allows me to buy some interesting things for testing. If you have any ideas about different objects you want to see, feel free to write in the comment below and maybe I will make a separate video about this. Now I'm going to get 0.1 microsieverts of radiation and eat the banana. Thanks for watching and see you next time.